Wormholes are fascinating theoretical constructs in physics that likely exist based on our understanding of the universe. They can be compared to black holes. However, instead of pulling everything into their depths and stretching objects into long, thin shapes, often referred to as spaghettification, wormholes provide a means to travel from one location to another in a shortcut through spacetime. To visualize a wormhole, imagine holding a blanket in the air. When you place a marble on the blanket, it creates a dip in the fabric, similar to how gravity curves spacetime according to Einstein's theory of relativity. If you were to fold the blanket in half and then push the marble down harder, it could potentially create a hole in the fabric and create a bridge through both layers of the fabric, forming a shortcut between two distant points. This is essentially the idea behind a wormhole. One of the strongest pieces of evidence supporting the existence of wormholes comes from Einstein's theory itself, which suggests that such structures are mathematically possible within the framework of general relativity. However, despite this theoretical foundation, we currently lack direct proof of their existence. We have yet to determine whether wormholes can actually be created or observed in reality. A significant challenge associated with wormholes is the requirement for exotic matter to stabilize them. Exotic matter is theorized to possess negative mass or energy, which is essential to keep a wormhole open and prevent it from collapsing under its own gravity. Unfortunately, we have not yet discovered exotic matter, and while its properties align with principles of mainstream physics, its existence remains speculative. Another interesting aspect of wormholes is their similarity to black holes, which can complicate efforts to distinguish between the two. Both structures warp spacetime, creating deep gravitational wells. However, a wormhole connects two different points in spacetime, whereas a black hole is a one-way passage into its singularity. This similarity presents a significant challenge in proving the existence of wormholes without physically traversing them, as the visual characteristics of both phenomena may appear alike. Additionally, wormholes bring intriguing possibilities for time travel. According to Einstein's theory of relativity, if one mouth of a wormhole were to travel at a substantial fraction of the speed of light, it would experience time dilation, meaning that time would pass more slowly for the moving mouth compared to the stationary one. As a result, when the moving mouth returned to the original location, a traveler could theoretically enter the wormhole from the slower-moving mouth and emerge from the faster-moving mouth at a different time. While the concept of building a wormhole time travel machine is intriguing, it's important to understand the limitations. If such a machine were constructed, it would only allow travel back to the moment the wormhole was created. This is because, while high speeds can slow down time relative to an outside observer, as per Einstein's theory of relativity, they do not actually enable travel back in time. In summary, while wormholes are theoretically possible and supported by the principles of general relativity, their existence remains unproven. The need for exotic matter to stabilize them and the challenges in distinguishing them from black holes make wormholes a fascinating yet enigmatic topic in modern physics. The potential for time travel through wormholes adds to their allure, inviting further exploration and speculation about the nature of our universe. The gravity within a wormhole would also be quite perplexing because, according to Einstein's theory of general relativity, wormholes involve extreme curvature of spacetime, similar to the intense gravitational pull of a black hole. As objects are pulled toward the wormhole, they would experience strong gravitational forces. However, once inside, gravity would become even more unusual. The curved walls of the tunnel, which define the wormhole structure, would create complex gravitational effects. Since gravity is essentially the bending of spacetime in Einstein's view, these curved walls would cause gravity to behave in unexpected ways. What makes a wormhole different from a black hole is that, unlike a black hole where the gravitational pull continues to intensify as the space becomes narrower and more compact, a wormhole's tunnel eventually opens up again at another point in spacetime. This prevents an object from being crushed by the increasing gravitational forces. However, to prevent the wormhole from collapsing under its own gravity, exotic matter with negative energy is theorized to be necessary. This exotic matter would act as a stabilizing force, counteracting the natural gravitational tendencies and keeping the wormhole open for travel.